Okay, thank you very much for the introduction. So, first of all, I would like to thank the organizers for inviting me to be here today. It's a great honor to take part of this symposium and of this special session, let's say, linked to the 10th anniversary of the EurASc program. So I will talk about, let's say, my EurASc grant and some of the results coming from the work that has already started 2 years ago. I changed a little bit the title, so I moved to a new era of cellulose-based electronics. I put it here, ionics as well. So not only based on paper, but nowadays based on cellulose composites, as the title of the grant mentioned. So I will start basically by putting some slides about the motivation about this work, and then presenting some of the results coming from the grant. Related with the development of electroconductive inks for sensing applications, some devices printed on paper, also made up of cellulose, and some electrolytes as well. And I will finalize with the most recent results that we are having regarding the application of of cellulose to photonic gate dielectrics, what we call photonic gate dielectrics. So also, let's say, take into account the title of the symposium, so better, let's say, materials for a better humankind, let's say. I will start by saying that we could take some great lessons from nature. So if you consider this kind of structure built by termites, inspired some engineers to build up some cooling systems on buildings. If you take the shape of the kingfish bird, inspired Japanese engineers to build up fast trains. If you consider, let's say, the shape of this plant, you can see that is the inspiration for the Velcro, let's say, adhesive. If you consider the shape of the shark skin, you see that it inspired boats for better hydrodynamics and also suits to improve the speed of the swimmers in the water. Indeed, this kind of structure, it's also very, let's say, important to avoid the proliferation of bacteria colonies. And this was also discovered due to the specific pattern of these small lamellas. If you look to the gecko feet, they have small hairs that could change the angle, and they could climb vertical walls, and immediately they could release from the wall. It could be released from the walls just by changing the angle of these small hairs. And this can be, for instance, implemented on vehicles, spatial vehicles or other vehicles that, to be used, let's say, on the surface of the planet, of course. And finally, because we had also yesterday something about the new revolution in industry, so where humans will basically share the space with robots, and there is a concern about the movement of the robotic arms due to the different axes required for the movement. You could see that engineers are also using nature as inspiration to create robotic arms without joints. So in terms of engineering, there is a lot of lessons that we have learned from nature. But what maybe is missing, and I put this statement, is something that we needed also to take into account, that also from the materials that we use, and if you consider 3 aspects of sustainability, we need to think on materials that are abundant, and if you can use biomaterials or nature-based materials, great for, say, modern technology. You need to think also on manufacturing processes. You need also to think how to get rid of these new technologies after the end life of these products. So what we propose is to move from this to something like this. So to create some disposable electronics that could be based on paper and cellulose. So just one introductory slide before moving up to the motivation of this work. So this is just, of course, an indication, but if you consider all the area produced, or the silicon wafers used for electronic devices, so if you consider all the area produced last year, it's about 6.5 million square meters. just to have an idea about the availability of paper substrates, so one single machine can produce this in less than 6 hours, the same area. Of course, when you think on electronics on paper substrates or flexible substrates, you are thinking on large area electronics, so you don't want to compete with computers or CPUs. But there are a lot of new applications and new simple electronic systems that can be built on paper. So it's widely available, and of course we know that it's recyclable. And of course it's based on, let's say, biopolymer, that is cellulose. Trying to converge, let's say, to paper electronics, of course, you need also to think on manufacturing processes that are cheaper and, let's say, less energy consuming. And of course, if you go for additive process that don't require special conditions, you need to think, of course, on printed electronics. And if you consider on printed electronics, you can also think that the investment, the initial investment to start, for instance, a company would be much less than to build a clean room to start to make conventional microelectronics. Of course, there are a lot of challenges when you go for printed electronics. Sometimes people think on combining several systems like displays, like memories, like sensors, like electronic circuits, everything on the same substrate, and this is very challenging. And requires different materials, different processing technologies sometimes. So, of course, this is not an easy way to go through. So, let's focus now on the, let's say, on the grant. So, the application of cellulose to build up these systems. Cellulose, it's a very abundant biopolymer, so it's the most abundant biopolymer existing on our planet. It can come from different sources, vegetal, from algae, from some small sea animals, and even from bacteria. Okay, and so how we can use this material to create substrates to print devices, electronic devices, but how we can use also cellulose to create active materials that could be used in sensors, in electronic devices such as transistors, or you could even build electrolytic membranes that can be used also in electronic devices, but you can also think on energy devices based on these cellulosic electrolytes. And of course, considering the market for large area electronics, there are lots of potential. But of course, you can also think on the holy grail of these markets, that is smart packaging and also biomedical devices, where the value is basically also due to the amount of devices that can be made and consumed. So let's say to summarize what happens, what relates with paper electronics or cellulose electronics, let's say. So paper as a separator in capacitors has been used for several years. Then people start to build up electronic devices based on organic semiconductors on paper, but it requires very expensive planarization process because organics are also very sensitive to the surface and they sometimes react with cellulose, and they are not much stable. Then in our group, let's say in 2008, under the coordination of Professor Elvira and Professor Martins, we started development of transistors, oxide transistors on top of cellulose substrates, paper substrates, I'd say. That was a breakthrough because it was possible to build devices with oxide semiconductors that are quite stable in contact with cellulose. But the next step, and it's what I propose in this grant, it's to move forward. So use cellulose as a truly electronic material, either by embedding some other functional materials or by creating different layers, like paper-like substrates, but with different functionalities along the entire thickness of the substrate. And so this is what should come from the project. So cellulose nanocomposites, low-cost devices and systems, and of course, things that are able to be recycled. Otherwise, it makes no sense to focus on this topic. Okay, so you can start from cellulose, polymeric chains. You can find it in different ways, like fibers, but you can find it also when you come from bacteria in a fiber-like structure, but much smaller in dimension, let's say 3 orders of magnitude smaller in dimension. But you can also start from microcrystalline cellulose. That's basically, let's say, already, let's say, treated cellulose, or also very interesting are the cellulose derivatives. So basically, it's the cellulose molecule, but where you change some of the functional groups, and you can modify it. especially to make them soluble in different solvents. And this is very useful because cellulose is not easy to dissolve. So if you change some of the terminal groups here at the chain, you can dissolve it in solvents like water, and this could be very interesting. And then you can blend, coat the fibers with other functional materials, as I told you. I have here two examples, carbon fibers and zinc oxide nanoparticles. But of course, you can add also conductive polymers, other carbon structures, like graphene, for instance, inorganic nanoparticles, as the oxide ones, or ionic liquids if you want to make some kind of membrane or substrate that is ionic conductive. So you can use either dissolved cellulose or fibers to combine with these materials to end up with some functional cellulose. So I will explain now the applications on carbon, let's say, fiber inks to be used as a sensing layer. I will not take much time on this, but just to explain that we mix a derivative of cellulose, that is carboxymethyl cellulose, that is soluble in water. We mix with carbon fibers, we prepare ink. Of course, if you think on printing technology, you have to take into consideration also the preparation of the ink. That is not also, it's also complicated sometimes because you need to adjust and get the proper viscosity and surface tension. You can print some electrodes with silver. You print this ink that is based on cellulose, and you create some sensing layers that look like teeth here in the pictures. After some printing steps, you have a continuous percolation path for current to flow through the carbon fibers. And when you have these kind of layers, you have a kind of porous structure that becomes more porous depending on the drying conditions, so if you dry too fast. And this is very interesting, for instance, if you want to use them as a humidity sensor. So cellulose, it's hygroscopic, so it will, let's say, absorb water from environment. And this will basically swell the printed layer and will affect the percolation of carriers between the different carbon fibers. So you can make a resistive, let's say, sensor that is able to detect the variations in a relative humidity made by printing technologies on paper substrates. They are also temperature sensitive, and they can also be, let's say, used for temperature sensors. But due to the large hysteresis, when you go up in temperature and cool down, you need to make a more complicated analysis, so you need a differential analysis, and this requires more complicated electronics to convert this into this variation in resistance to a temperature value, but it's also possible. So if you go for the transistors now, that is the basic element for electronic circuit. In this case, we also use another derivative of cellulose. It can be ethyl cellulose, but this is soluble in more nasty solvents like toluene. But again, recently we were able to replace this by CMC, so go back to water solvent system that is much better from the environmental point of view. And there is also some footnote that I would like to add. So if you think on upscaling things for industry, you need also to think on what you can use in a real industrial environment. And solvent is a big concern, for instance, in printing industry. It's a big concern for the workers' unions. So let's go back to the paper transistors now. So you print a source and drain electrodes. Basically, you need 3 electrodes to operate these devices. So this is basically where the current will flow. Then you put the semiconductor, so that will basically allow the current to flow between these 2 electrodes. You put a dielectric layer. In this case, this is electrolyte. I will explain briefly how does it work. And then you put the 3rd electrode that will basically control the charge that you induce in the semiconductor and controls the current flowing between the two bottom electrodes. Just very briefly, so electrolytes instead of normal dielectrics, you can build up huge capacitance using this kind of structure, basically electrolytic capacitance. You have an electrolyte with ions. You can displace these ions, keeping the charge neutrality in the bulk, but accumulating ions at the interfaces. You have charge separation here. You induce opposite charge in the semiconductor, so you have charge separation in a very narrow space, so very big capacitance can be built up at these interfaces. So this means with very low capacitance that with very low voltage you can operate these devices. But this is very good if you want to think on printed systems or autonomous systems. This is how the printed layers look like depending on the zinc oxide content. Okay, so we mixed we mix the CMC with zinc oxide. You can change the content of zinc oxide nanoparticles in the ink. And after printing it, we have these kind of devices on paper substrates, which, with this, let's say, printed layer that is made of CMC and zinc oxide. This is dried at room temperature, so you don't need very time-consuming annealing process to put these devices operating. And you see, they operate between 0 and 2 volts on this electrode that controls the charge or the free carriers in the semiconductor. Normally, when you look to a transfer curve of a transistor like this, it's important to see the relation between the maximum current and the lowest current. Also to see the voltage at the transistors will change from the off state to the on state, how fast this happens. And so you can see you can operate these from 0 to 2 volts. And they have proper characteristics, so the on-off ratio current here is already above 3 orders of magnitude. Of course, you can go to make also more complex, let's say, but still simple circuits like current mirrors or inverters based on these devices. So these are, let's say, the building blocks for electronic systems. Also using zinc oxide, in this case, written on cellulose, and I will explain why written. So you can go for simple deposition process that in this case uses a pen. This is a rollable pen that has already been demonstrated, say in the past, that can be used to print silver layers or to write silver layers to create some antennas, some simple antennas. But the most difficult part on this, let's say, area is indeed to print the good semiconducting layers. In this case, we are using a calligraphic pen that you prepare a special ink based on zinc oxide, and you can write these layers on paper. This is here on the right-hand side. You have a picture how these layers look like on top of cellulose fibers. So these cellulose fibers, this is the layer made of zinc oxide nanoparticles. So they have also a precursor that will create a matrix, amorphous matrix in between the zinc oxide particles, so you can improve the conductivity or reduce the impedance of this layer. And from these, you can create also devices on transistors on paper. They operate at higher voltage at the moment because we are using the paper itself as a dielectric and is not that good ionic conductor as the membranes that I will show later. But we can also make the same with these electrolytic membranes nowadays, so reduce the operation voltage. If you, for instance, use also a pencil to write a resistor, you can create a fully written electronic circuit. So one of the topics is these electrolytic membranes and why they are very interesting. They can be used in the transistors, but they can also be used, for instance, in energy devices. We are not still working on this topic, but there is also possibility of using them on batteries or supercapacitors. And basically use microcrystalline cellulose again, CMC and carboxymethyl cellulose, you mix both, and this CMC is used to give more, let's say, mechanical strength to the final membrane. One of the key issues is the dissolution of the cellulose, as I told you before. So in this case, we use hydroxides, metal ion hydroxides that are not so aggressive as the normal solvents for cellulose. And this is an ion source as well. So the ions will stay in the membrane and will basically improve the ionic conductivity of these membranes. So you need to neutralize these at the end because if the membrane has a very aggressive pH, it will destroy the semiconductor layer. And you can shear cast and make these membranes by shear casting, is how they look like. And I will skip the video just by questions of time maybe. The most important message here is how stable they are over time. So this is the initial behavior of the transistors where you use these membranes as dielectric, let's say, and how they look like after 40 days just kept on the office table. So they are environmental stable. And one very important point here, they can be recycled. And what I mean about recycling. So you take the membrane, you dissolve it again in the solvent, and you form a new membrane from the same, let's say, raw material, and you get similar performance when you use it on devices. Okay, so I will just, this is the way we make it. So we cut the membranes, we put in the transistors, we detach them from the transistors, and you can recycle and this can be, let's say, made over and over, and up to 5 times, 10 times, it will still work. I will just finalize, so 2-3 minutes just to say about the most recent results on using cellulose also to create photonic dielectrics. So again, this is a kind of inspiration from nature, because we can see that some specific structures give some what we call structural colors. Sorry, this because I will just try and say, okay. And these membranes have, this is passing in automatic way. These membranes have a structural color coming from the arrangement of the cellulose nanocrystals. They are based on cellulose nanocrystals that are obtained from hydrolysis. So if you dissolve a cellulose fiber, it contains amorphous and crystalline part. You take only the crystalline part, you will end up with a cellulose nanocrystal that has a small charge coming from the process that is used to create these crystals. And they, when you let them assemble, self-assemble, they will self-assemble with a chiral structure. So there is a rotation of the crystal orientation along the different planes. So you end up with something like this. And these chiral structures are very interesting because they can reflect polarized light, depending if it is left-handed or right-handed circular polarized light. So if you make some membranes with this chiral, let's say, if you use these nanocrystals to create some chiral membranes, you can create some devices also using these as a dielectric. So what we have tested is the addition of different types of ions, lithium, sodium, and potassium. And what we realize is indeed that they can be used as a dielectric on transistors. This is the characteristics of the transistor, so with mobility very close to the normal dielectrics that you can get on these kind of materials. Very nice characteristics, almost no hysteresis, especially when you use potassium. Okay, we can then discuss this after, but what we realize is that the potassium ion, it's supposed to be the biggest one, is what results in a better performance. So we took profit of the chirality and it's what we're trying to prove, to allow a better, or to facilitate the movement of the ions inside the structure, so to increase the ionic mobility. And this results better with potassium indeed. So you can replace lithium by some more friendly, let's say, ions like sodium and potassium. And of course, this is the final slide, so just for the future perspectives, what we are trying to do now, it can reflect circular polarized light and reflects left-handed. So for chiral selectivity, it can be used as a sensor. And this is very useful because you know that some molecules, this is very well known, that is DNA, and also some drugs. Chirality is important. For instance, if you want to select some pharmaceutical drugs, depending on the chirality, or if it is left-handed or right-handed, you can have a drug that is good for you or can be bad for you, or it can have, for instance, one application for anti-HV agent, or other different application depending on the way the molecule itself arranges. And also, we can use this to template some inorganic materials to create chiral semiconductor layers that itself they can detect circular polarized light. So I will just leave you with the final, let's say, video with some, let's say, concept. Already we're integrating some of printing sensors, printing transistors, printing electrochromic displays. So we hope in the future to improve a lot these kind of systems. This is a temperature sensor that will detect temperature changes. The transistor will open. You will have a message appearing. In this case, it's gas detection because we could not make gas testing in our lab. So, but the initial plan was to build up a gas detection tech. And of course, I would like to acknowledge to the team at CENIMAT. So it's a real good environment to work, and we have here the responsibles for that, Professor Fortunato and Professor Martins. But of course, special word to the guys that do the hard work. They are pretty happy, except one. It is very focused and concentrated, but you can guess who is the German here. So thank you very much.